So studying for the HPE7-A11 exam is, well, it's a lot like preparing for an advanced driving test.
Right, but like during a hurricane.
Exactly. It's not just about knowing, where the steering wheel and the brakes are.
Yeah, you have to actually understand the physics of the road when everything inevitably goes wrong.
Right. You need to know how the network handles when it's totally overloaded.
Or
Yeah.
when a critical link fails.
Or when a massive wave of legacy devices just suddenly connects all at once. So, welcome to the deep dive. And our mission today is to equip you with the exact problem-solving logic to just absolutely conquer this exam.
And that logic is, it's everything. The test really doesn't care if you've memorized flashcards.
No, not at all.
It's designed to test your real-world application of these complex Aruba network designs. You have to prove to them that you understand the architectural intent.
So before we get into the really heady engineering, let's just quickly look at the baseline specs for what you're walking into.
Good idea.
The HPE7-A11 is a proctored exam. You've got exactly 2 hours to get through 70 questions.
Which goes by fast.
So fast. And you need a 66% to pass, and it's delivered entirely in English. So it's a solid block of time.
Yeah, it really is.
And to help you understand those network physics we talked about, we're going to dissect 10 specific practice questions from our source material today.
We'll read the exact scenarios you'll face and break down why the distractors are, really dangerous traps in the real world.
Right. So we need to start at the foundation.
Yeah, before a network even goes live, how do we prevent disastrous typos from bringing down a production environment?
Oh man, the dreaded typo.
Right. We have to look at centralized validation before we push dynamically to the edge.
Okay, so let's jump straight into the first scenario. The exam is going to throw a situation at you that reads exactly like this. Quote, a network engineering team manages a large fleet of AOS-CX switches. They need a tool to validate configuration changes before deploying them, ensuring no syntax errors or policy violations occur. Which Aruba management solution provides this specific pre-deployment validation capability?
So when you're sitting in the exam room, your brain is going to want to jump to the most famous management tools, right?
Naturally.
The competing approaches they offer you here are Aruba Central Cloud, ClearPass Device Insight, Airwave Management Platform, or Aruba NetEdit.
Okay, so I know ClearPass Device Insight is amazing for visibility.
Yeah, totally.
Like figuring out exactly what devices are plugged in. But it doesn't simulate code, so I'm immediately tossing that out as a trap.
Exactly. It's a complete trap.
And Aruba Central and Airwave are phenomenal for massive, global management. But they don't do what the question's specifically asking for, do they?
No, they don't. They lack that highly specific, localized simulation environment for switch code.
Right.
This question is hunting for Aruba NetEdit. NetEdit is purpose-built for managing and validating configurations specifically on AOS-CX switches.
Which is key here.
Yeah, it actually lets engineers deploy changes in a sandbox environment first. It checks for syntax errors and, policy violations before you ever touch production.
Which is huge.
It is. It drastically reduces the risk of taking down an entire data center just because somebody missed a semicolon in the CLI.
Oh, I've been there. So NetEdit is basically a really advanced spelling and grammar checker for complex network code.
That's a great way to put it, yeah.
It highlights the squiggly red line, showing you the logical errors, before you hit send on an enterprise-wide configuration.
Exactly. And that centralized validation is what allows us to safely automate the edge of the network. Which, by the way, brings us to a huge theme on this exam.
Which is zero-touch provisioning.
Spot on.
That sets up our next scenario perfectly. So listen to this requirement. Quote, an organization wants to simplify edge switch configuration. Instead of manually configuring ACLs and VLANs on every access switch, they want the switch to dynamically receive the entire policy configuration for a user at the moment of successful authentication. Which feature provides this capability?
And the architectural options they give you to solve this are local user roles, static port security, downloadable user roles, or global policy enforcement.
Okay, so break this down for us.
Well, this is a classic test of catching manual versus dynamic solutions. Local user roles and static port security are just terrible choices here.
Because they're manual.
Exactly. They represent the exact manual, switch-by-switch, port-by-port configuration that the prompt specifically states the organization wants to avoid.
Right, the prompt explicitly says, instead of manually configuring.
Yeah. And global policy enforcement, it sounds like a great corporate buzzword.
It sounds very official.
It does, but it's just a generic distractor term in this specific AOS-CX context.
Okay, which leaves downloadable user roles as our solution. But let me push back on this for a second.
Sure.
Because as an engineer, this sounds kind of terrifying. Isn't it incredibly risky, or at least really slow, to force the switch to dynamically pull the policy down from a central server every single time a user plugs in?
I get that.
Like, rather than just hard-coding the VLANs into the switch ports once and being done with it.
Your instinct to protect the edge is totally right, but the reality of enterprise scale is the exact opposite. Hard coding is mathematically riskier because humans make errors.
Ah, the human element.
Right. Imagine updating thousands of switches manually because your security team changed one single firewall rule.
That would be a nightmare.
It's awful. With downloadable user roles, the switch dynamically pulls full policies, like VLAN's access control lists, from a central server like ClearPass, the exact millisecond a user authenticates.
Oh, wow. So you fix it in one central location and it's fixed globally.
Precisely. The, millisecond of download time is entirely worth the guarantee of zero-touch, error-free edge provisioning.
Okay, that makes total sense. So we've automated the local edge. But here's where the physics of the road get really complicated. What happens when the network's edge isn't a cubicle, but like someone's living room?
Yeah, or a building shared by entirely rival organizations.
Oh, right. So we're moving into borderless networks.
Which is a massive focus for modern IT and definitely for this exam.
Let's look at the remote worker scenario then. The STEM reads, quote, "A company has hundreds of remote workers who need secure access to corporate resources from their home offices. The company wants to send pre-configured access points to the workers that automatically establish secure tunnels back to the corporate network without requiring local IT expertise. Which architecture best fits this need?"
And they give you 4 options here.
Right.
Campus ATs connected to a local mobility controller, microbranch APs managed by Aruba Central, remote APs terminating on a third-party VPN concentrator, or instant APs operating in a local virtual controller cluster.
Okay, so when you read that STEM, your eyes should lock onto the phrase, "without requiring local IT expertise."
All right. Absolutely. That is your ultimate constraint. If you introduce a third-party VPN concentrator into the mix, you almost always require manual configuration.
Right, like complex key exchanges.
Exactly, or even client software installation. That immediately ruins the zero-touch requirement, so we can just throw that option out entirely.
Makes sense. And campus APs rely on a physical local controller, right?
Yep.
While instant APs rely on a local cluster of other APs. Neither of those makes any sense sitting alone on a desk in a solitary home office.
Right, it's just one person at home. Which brings us to microbranch APs managed by Aruba Central. They are purpose-built for this exact teleworker situation.
How does it actually work for the user?
You basically ship the hardware to the house. The user plugs it into the regular consumer modem. It reaches out to the cloud via Aruba Central and automatically establishes an IPsec tunnel back to corporate.
Wow.
Yeah, 0 IT degree required for the remote worker.
Plug and play at its absolute finest. But what if the shared space is physical? Like 2 companies in one building?
That happens all the time.
Yeah, the exam presents this scenario, quote, "A government agency shares a building with a private contractor. Both organizations want to use the same physical access points, but they require their wireless traffic to be completely isolated and terminated on their own separate management gateways. Which feature should the architect recommend?"
Okay, the competing approaches are multi-zone, dynamic segmentation, virtual extensible LAN, or advanced cryptography.
This is a phenomenal architectural challenge, actually.
It really is, and the distractors are incredibly sneaky here.
Well, advanced cryptography is a given in modern networks, right?
Okay.
But encrypting data doesn't physically isolate management gateways.
Exactly. And virtual extensible LAN, or VXLAN, is a tunneling protocol, but it's used in the wired core or the data center for overlay networks. It is not the specific Aruba feature for splitting wireless gateway management.
I feel like dynamic segmentation is the real trap here, though. I mean, it sounds like it segments things.
And that's exactly why they put it there as an option. Dynamic segmentation is brilliant for unifying wired and wireless policy, tunneling wired traffic to a gateway,
Okay.
but it does not separate wireless traffic into completely different isolated tenant gateways. Multi-zone is the feature you need here.
So how does multi-zone actually achieve that, like mechanically?
Multi-zone allows a single physical access point to broadcast multiple SSIDs,
Okay.
and then it builds entirely separate, secure GRE tunnels for those SSIDs to totally different mobility gateways.
I love that. It's like having 2 completely separate plumbing systems safely flowing through the exact same physical pipe.
That's a perfect analogy.
The AP is the pipe. But the data from the government agency goes to a completely different water treatment plant than the data from the private contractor. The water never mixes.
Exactly. And that exact physical and logical separation is what satisfies strict government compliance audits.
Speaking of sharing physical spaces, modern networks don't just share space with other organizations. They have to share the airways with devices from totally different technological eras.
Oh yeah, the generational gap of IT. It's a real headache.
And security protocols are where those generations clash the hardest.
Without a doubt.
The exam tackles this head-on with this question. A financial institution is upgrading their wireless security to WPA3 Enterprise. They have a mix of legacy barcode scanners that only support WPA2 and modern laptops that support WPA3. How should the architect design the SSID to accommodate both without compromising the security of the modern devices?
And the options to weigh are: create a single SSID using opportunistic wireless encryption, create a single SSID configured with WPA3 Enterprise Transition Mode, deploy MA authentication as a fallback for the legacy devices, or configure a captive portal exclusively for the legacy barcode scanners.
Okay, so security questions are all about finding balance without creating massive loopholes, right?
Right. And MA authentication, fallback, and captive portals are just terrible choices for a financial institution.
Yeah, that sounds super insecure.
You are basically bypassing true enterprise-grade encryption just to get old barcode scanners on the network. That violates every compliance rule in the book.
Definitely. An opportunistic wireless encryption, or OWE, that's designed specifically to provide encryption for open, unauthenticated networks.
Yeah, like a coffee shop network, not a bank.
So WPA3 Enterprise Transition Mode is the intended answer. But I have a serious bone to pick with this approach.
Oh.
Yeah. Why bother with transition mode? As an architect, why wouldn't I just broadcast two separate SSIDs? One called, I don't know, Finance Old, specifically for the scanners, and one called Finance New for the laptops. Just keep them totally apart.
That is such a common trap architects fall into, and it comes down to the physics of RF performance.
Okay, how so?
Every single time you broadcast an SSID, the access point has to send out management frames, which are called beacons, roughly 10 times a second.
9 times a second.
Yeah.
Wow.
Yeah, just to advertise that network. And to ensure every device can hear them, these beacons are sent at the lowest possible data rate, which is usually just 1 megabit per second.
So it acts like a traffic jam for the airwaves.
A massive traffic jam. It's called SSID overhead. If you broadcast 5, 6, or 7 SSIDs, a huge percentage of your available airtime is consumed by the access points just slowly shouting their names.
Leaving very little room for actual payload data. That makes so much sense.
Exactly. Transition mode securely allows both WPA2 and WPA3 clients to negotiate their connection on the exact same SSID.
So the old scanners get the WPA2, they understand.
And the laptops get the hardened WPA3. And you save your precious airtime.
That is a crucial connection to make. Because security is one invisible layer of the network. But the physical radio waves are another invisible beast entirely.
Oh, absolutely.
Which brings us to the invisible traffic cops. Managing the physical airspace. This is where things get really crowded. Listen to this scenario. Quote, in a dense university lecture hall environment, the network administrator reports frequent co-channel interference and suboptimal channel assignments. The environment is fully managed by Aruba Central. Which service should the architect rely on to dynamically optimize the RF environment over time?
And we have to choose between Air Match, Client Match, Adaptive Radio Management, or Wi-Fi Clear Connect.
Okay, so this question is definitely testing your ability to differentiate between very similar sounding proprietary features.
It is. Let's clear the junk first. Wi-Fi Clear Connect is a completely fictitious distractor.
Made up entirely.
Right. Adaptive Radio Management, or ARM, is real, but it's the older, localized legacy version of RF optimization, and the prompt specifically highlights Aruba Central Management over time.
So it's a showdown between Air Match and Client Match.
And this is where test takers always trip up. Client Match is a trap here because it steers the clients.
Not the channels.
Right. It does not optimize the channels or the transmit power of the access points themselves. AirMatch is the correct answer. Okay. AirMatch is the cloud-based AI service in Aruba Central that analyzes environmental telemetry over a 24-hour period. And then it dynamically calculates a new global plan for channel and power settings to eliminate that co-channel interference.
We got it. So AirMatch manages the global environment. But what about those individual devices? Because the very next scenario addresses that directly.
Let's hear it.
In a high-density environment, several legacy wireless clients are persistently connecting to access points that are far away, even when a closer AP has a stronger signal, causing poor performance for everyone. Which Aruba proprietary technology is designed to proactively guide these sticky clients to the optimal radio.
And the options are APRF, air group, air match, or client match.
Now we are looking at the client side of the physics.
Right. Legacy devices are notoriously sticky. Their internal roaming algorithms are just really weak.
So they grab on to the first access point they see in the lobby.
And they refuse to let go, dragging their connection down as they walk across the entire building.
So annoying.
Yeah. Now, APRF gives you visibility into applications, not RF steering. Air Group manages MDNS protocols like Apple Bonjour, which is totally unrelated.
And, as we just established, Air Match optimizes the overall RF grid, not the individual sticky client.
Leaving us with Client Match as the solution.
I picture Client Match as, like, a very polite but highly trained bouncer at a club.
Ha! Okay, I like that.
You're crowding the bar in the back, straining to get a drink, and Client Match taps you on the shoulder, utilizing protocols like 802.10 fee, and says, "Excuse me, I'm severing this connection and escorting you to an empty register right over here so everyone gets served faster."
That is pretty accurate, and it does that seamlessly on a packet level to balance the load.
But what happens when the traffic isn't just crowded, but extremely time-sensitive, like real-time voice calls?
That's where quality of service comes in.
Right. The exam tests quality of service, or QoS, with this scenario. An enterprise is deploying a new unified communications platform. To ensure high-quality voice calls across the campus network, the architect must ensure voice traffic is prioritized. Which action should the architect take at the campus access edge?
And the competing options here are remark all incoming traffic to the highest priority queue regardless of origin. Drop all traffic that does not have a trusted voice tag. Trust the DSCP markings from recognized voice devices and place them in a strict priority queue, or encrypt the voice payload to prevent intermediate switches from delaying the packets.
Okay, let's dissect these. Encrypting the payload adds processing overhead, but it does absolutely nothing to prioritize the packet's placement in a switch queue, right?
Nothing at all. It's a security feature, not QoS.
Okay, but as someone who wants to guarantee voice quality, dropping all traffic that doesn't have a trusted voice tag sounds incredibly effective. Clear the lanes entirely. Why wouldn't I just do that?
Because you would cause a catastrophic network failure.
Wait, really?
Yes. If you drop all untrusted traffic at the edge, you are destroying every single email, file transfer, and web request just to make sure a phone call goes through.
Oh. Yeah, that is wildly destructive.
Very.
Fair point. What about just remarking everything to the highest priority?
Well, think about it. If everything is a priority, nothing is a priority. If you force all traffic into the top queue, your delicate, delay-sensitive voice packets are still going to be stuck behind massive gigabyte file downloads. You have to use classification and policing.
So trusting the DSCP differentiated services code point markings specifically from recognized voice devices and placing only that traffic into a strict priority queue.
That is the only way to mathematically guarantee low latency for real-time communications.
Wow. Okay, so all of these brilliant edge optimizations, the strict priority queuing, the client match steering, the dynamic user roles, they mean absolutely nothing if the core of the network collapses.
The backbone. If the core fails, the edge is irrelevant.
Let's look at worst-case scenarios and the heavy lifting at the center of the architecture. The exam tests extreme high availability with this scenario. A hospital requires extreme high availability for their wireless client traffic. If a wireless gateway fails, the client sessions must fail over to a standby gateway without requiring the clients to re-authenticate or renew their IP addresses. Which feature must be enabled in the design?
The options are Layer 3, roaming across disparate subnets, fast BSS transition on all access points, VRRP backup master state synchronization, or stateful hitless failover within the gateway cluster.
The stakes in this scenario are literal life and death.
They really are. Think about mobile medical monitors transmitting patient telemetry. Layer 3 roaming and fast BSS transition, which is 802.11r, are standard features for a client moving between access points.
Right.
They do not solve the problem of the central gateway itself crashing.
What about VRRP? Virtual Router Redundancy Protocol is literally designed for router failure.
It is, but VRP only moves the default gateway IP address to a backup router. It does not sync the firewall session tables or the encryption keys.
Oh, I see.
Yeah, if you use standard VRP and the gateway dies, the client device has to completely rebuild its TCP connection. The medical monitor goes offline.
Which is unacceptable in a hospital, so
Yeah.
it has to be stateful hitless failover.
Yes. Stateful is the magic word here. It means the exact session state, the encryption keys, the active firewall flows. Everything is constantly mirrored in real time between the active and standby gateways in the cluster.
So if the primary gateway literally bursts into flames,
So if the primary gateway literally bursts into flames?
the standby assumes the load hitlessly.
Wow.
The TCP connection never drops. The medical monitor never even knows the hardware failed.
That is incredible resilient engineering.
Yeah.
So what does the routing architecture look like that supports all of this at a massive campus scale?
That brings us to our final scenario.
In a modern spine-and-leaf campus core design using AOSCX, what is the primary advantage of using multi-protocol BGP over OSPF as the underlay routing protocol? And the options to evaluate. It scales better for a massive number of equal-cost multipath routes and provides granular routing policy control. It converges significantly faster than OSPF during a single link failure in a small network. It automatically discovers neighbor relationships without any manual configuration, or it operates exclusively at layer 2, simplifying the overall network topology.
Let's clear the technical traps immediately. BGP operating at layer 2 is entirely false.
Right, completely false. BGP is the definitive layer 3 routing protocol of the internet.
Okay, and the auto-discovery option is also wrong, because BGP famously requires explicit manual neighbor configuration, unlike protocols that auto-discover peers via multicast.
Spot on.
And what about convergence time?
That's a very tricky trap. OSPF actually calculates and converges faster than BGP when a single link fails in a localized network.
Really, so that leaves the scale and policy control as the primary advantage.
Exactly. In large data center or massive campus cores with spine and leaf designs, you have an underlay network with dozens of physical paths that cost exactly the same to reach a destination.
Yeah.
BGP is designed to handle that massive scale of equal cost multipath or ECMP routing. Furthermore, BGP lets you filter and manipulate routing policy with a level of precision that OSPF's shortest path logic just cannot match.
I look at OSPF like a really detailed local city map.
Okay.
It finds the shortest path and it updates quickly if a street is closed.
Yeah.
But BGP is the massive global air traffic control system you need when you have thousands of equal cost flight paths crossing a continent.
And you need to tightly control which airlines use which corridors.
Exactly.
That analogy perfectly captures the architectural intent, and that intent is what you really must keep in mind for the HPE7-A11.
Absolutely.
Passing this exam, as we've seen across these deeply technical scenarios today, isn't about memorizing acronyms. It's about understanding the mechanics.
Right.
Whether you are configuring stateful failover to keep a hospital's life support monitoring online or setting up multi-zone tunnels to isolate government data, you are designing the invisible infrastructure that keeps the modern world running.
So when you are sitting in that exam room, every time you see a scenario, ask yourself, what is the underlying physical or logical problem this protocol was actually built to solve?
That's the secret to passing.
But I want to leave you with one final thought to ponder, building on everything we've explored today. If tools like downloadable user roles and NetEdit are already using central logic to automate the edge,
Right.
and AirMatch is using cloud AI to manage the physical radio waves, how long will it be until AI takes over the core routing decisions entirely?
Oh, wow.
Just imagine a massive spine-and-leaf BGP architecture that doesn't just route traffic, but is completely self-configuring, self-healing, and dynamically rewriting its own policies faster than any human engineer ever could.
That changes the entire physics of the road we're driving on.
It really does. Keep questioning the infrastructure around you, keep studying those network physics, and we will see you next time.